At Hot Chips this year, AMD gave a Zen 3 microarchitecture presentation. Pretty much what we'd seen before, we weren't expecting anything new. However, there is one slide which gives us new information which may limit how AMD scales its core chiplets in the future.
What's your minimum specification?
If you want an independent cloud services provider for home servers, VPNs, or clients, consider Linode and sign up today at linode.com/techtechpotato for a free $100 60-day credit. A recent Gartner performance report shows Linode's topology offers almost double the database performance per dollar than other public cloud services. So this video is going to be in two parts. First of all, we're going to go through how things can be connected to each other in terms of rings and crossbars and meshes and stuff. If you know all about that, then go on to section 2, where we discuss exactly what AMD presented and why it's limiting for them. But first up, section 1. So for this section, I've created some slides that we can go through. Now, think about when you're connecting two elements together. What's the easiest way to connect them? Well, just A to B. You have a simple point-to-point two-element connection. When that moves to 3 elements, you can still do a same point-to-point connection, and you can have each of your elements connected to each other. This is what we call a fully connected topology. When you move to 4 elements, it gets a bit different. So here we have 2 examples of how to connect 4 different elements. On the left, we have a ring, which is just a simple square in this case. And then on the right, we have a fully connected 4-element design. Now, the difference between the two is that each of these elements, the ring only has 2 connections, while the fully connected, each element has 3 connections. That means you arguably are going to be using 50% more power in the fully connected design. However, because the fully connected design means that you only have to hop once to each other element, then you've got a lower latency. Whereas with the ring, you have 1 hop to 2 different elements. To this one, whereas if you want to go to this one, you require 2 hops. So your average hop length is actually 1.3. So your average hop length is 1 plus 1 plus 2, 4 divided by these 3 elements. So you've got an average hop length of 1.33. So your latency increases, especially if you want to go to this one, but your power is decreased. There's also an issue of bandwidth. With the ring, you have 2 connections, and so for the fully connected, you have 3, so arguably you'd have a 50% more bandwidth. But also, you have non-blocking in a fully connected design. If you need to go somewhere, it has to go straight from point to point. If other elements in the ring require that bandwidth, then you may have contention issues. This is where it's important to say that when we mean a ring, you have on the left here just a simple ring that's unidirectional. But in actual fact, most modern rings in modern architectures are bidirectional. You can go either way. Intel, in its most modern architectures with rings, actually has 2 rings that can both be bidirectional. This means you can double the bandwidth around the ring, but you can turn one of the rings off when you want to save power. Moving on from 4 elements, we can go up to 6 elements, where we have on the left again a ring, which is very simple, very straightforward. Whereas on the right, we have a fully connected 6-element design. So in this case, each element has 5 connections. You still have that 1 hop latency, but now you're having to deal with the power of having all 5 of those connections. With a ring, you've still got 2 connections, so it's fairly consistent on the power front. However, you now have more hops to get anywhere. So if we consider this top left element, you've got 1 plus 1 plus 2 plus 2, which is 6, plus 3, which is 9, divided by these 5 elements, and you have an average of 1.8 hop latency, depending on where you want to go. This is why it's important to consider a ring of 6 elements being bidirectional rather than unidirectional, because if it's unidirectional, then your number of hops you need to get to another element is going to take longer. Now, of course, this can scale up. We have 8 elements. I'm not doing the fully connected design here, but 8 elements, this looks like an Intel ring. We're very familiar with this concept. However, the ring is not always cores. If we're saying elements are cores, different elements in this design could perhaps be memory or integrated graphics. Intel doesn't often say what all of the different stops are on its ring. Usually we say each element is a ring stop in the ring. So it's very easy to consider that an Intel architecture design, say Rocket Lake, would be 8 cores. Therefore, there's 8 elements in the ring, but actually you've got DRAM, graphics, you've probably got an I/O there. And if there's anything else, say anything integrated that Intel doesn't want us to know about, or encryption engines or something like that, then that will also go on the ring. Now, if you have more and more elements, rings get impractical. The number of average hops you need to do gets way too high. Then you're also limited in bandwidth. So what a number of architectures do, such as Intel and ARM, is that they use a mesh, kind of like this. We've kind of seen these in Skylake, Cascade Lake, Ice Lake, and next generation Sapphire Rapids. It's just a 2D mesh where you can access everything arguably in a number of ways. If one way is blocked due to high traffic, you can arguably go around a different way. This is meant to be a trade-off between sort of power and connectivity and latency. As you can see, we've got 4 lots of memory coming off of this design. And you can cluster these, you can have subnuma clusters, you can put things into quadrants to make those cores have lower latency to specific memory. But the idea is that you've got a balance, and you can arguably cut this up into chiplets, which is what Sapphire Rapids is doing. Now, if you've got 8 elements, Intel in its 8 socket platforms does what's called a twisted hypercube, which is this, which is, imagine 8 points in a cube. You're connecting both the rings. Then in the top layer, you're connecting those directly. And the bottom layer, you're connecting those inverted. They call this a twisted hypercube. And this means that every processor in the design has 3 connections. If we go back to the mesh, you see that some elements have 2 connections, some have 3. On the edges, on the corners have 2, on the edges have 3. In the center, they have 4. So you have elements with different numbers of connections that varies your latency across the mesh. Whereas with the twisted hypercube, the idea is that with your 3 connections, you have your single processor here, that's considered the top left again. You have this processor, and this one over here on the right are all connected by 1 hop, and then the other 4 are connected by 2 hops. So that this has an average hop latency of about 1.58. In next generation Sapphire Rapids, Intel has said that the processors will now have 4 direct connections. So you'll now have 4 processors that are 1 hop away, and then 3 processors that are 2 hops away. That reduces your average hop latency to 1.42. And Intel has decided that the trade-off in power for the decreased latency is worth it. Now, there is another element between rings, direct connections. We have crossbars, and a crossbar is meant to be, look in a simple diagram, kind of like this. You connect all of your elements together to it, and it just sorts itself out. Now, this is arguably a bit of a hack, because what you've done is you've moved the problem to the crossbar. You could say that in this case, each element only has 1 connection, so that saves on power. But now your crossbar, depending on where it is, may itself be the source of the power requirements. So when we're talking about inside a CPU, the crossbar might be in silicon. But if we're speaking about outside of the CPU or even the GPU, then the crossbar might be itself a separate piece of silicon. Kind of think like an NV switch. When you've got those big AI-enhanced NVIDIA clusters, you have your A100s set out on your board, but they have to connect to all the other A100s, and they do through NV switch, which is, essentially a crossbar. But there are different types of crossbar. You can have a ring crossbar, which is essentially making a ring out of all the elements, and you can attach, as I've shown in the diagram, memory or PCIe or different accelerators. Your elements don't have to be CPUs. They could be other chiplets with GPUs or FPGAs. And then beyond the ring crossbar, you also have a switching crossbar, which kind of looks like a mesh. And the idea is that it's very easy to connect everything to everything else. In this scenario, the idea is that every CPU has, say, full access to memory, full access to PCIe, and the average latency should be reasonable. Now, the switching crossbar looks like a mesh, but there are actually other ways. If you had a little bit of 3D, you can connect them differently. So there are research papers talking about how you can connect things rather than in a simple X and Y direction, in a torus, in a butterfly, in something called a butter donut. which is a combination of the butterfly and the torus. And the idea here is that you're meant to globally minimize your interactions within the mesh, minimize how many hops you have to do to minimize your latency. And all of these designs can be configured based on how many nodes you have, your links, the diameter of your effective mesh, and your average hop. So in this example, the standard mesh 6x4 would have an average hop of 3.33 right at the top here. Whereas moving down to the butter donut, you essentially reduce one hop. You have slightly fewer links, there's slightly fewer nodes, but your bisection bandwidth as well is tripled. So making links in a mesh is easy because everything is either in the cardinal directions, forward, back, left, or right. With these designs, you have to end up putting connections over and above and below each other. Now that's easy enough to do in silicon, hard to do as a separate physical design, unless you're breaking out, say, into that crossbar. And the idea here is that if you have, say, an interposer, you can implement some networking logic on the interposer and just put, say, chips on top of that, which is something we're going to come to. But first, let's go on to AMD. So I've made a few videos on this channel about hot chips. Really great event. You should all attend if you can. But as part of the AMD Zen talk, we were shown this slide. Now, cast your mind back to Zen 2. Zen 2, as shown on the left here, we had 2 4-core complexes. And each of these core complexes was fully connected. Each core was connected to each other core with minimal latency, maximum bandwidth in a fully connected design. And then each of these core complexes would move out of the Infinity Fabric to access the I/O die and your main memory. With Zen 3, they went from a 4-core CCX to an 8-core CCX. And there was always the question of how are these 8-core complexes connected? Are they a fully connected design like we'd seen on Zen 2? Or has AMD gone for something else? Now, AMD was very, very coy about saying anything about the design. They asked if it was fully connected, if it was a ring, if there was something else. And they basically said it's not fully connected, but it essentially acts like it's fully connected. And when we did testing at AnandTech to see the core-to-core latency, we essentially saw what was an effective fully connected design. So at Hot Chips, the chief architect of Zen 3 presented this. It's a ring. New bidirectional ring bus. High bandwidth, low latency, 32 bytes in each direction. This is a bit weird. We weren't expecting a ring. Our results certainly didn't show a ring, so maybe there's some secret sauce in here. So that being said, what it does mean is that if we scale this up to EPYC, with rings in the chiplets and a ring in the I/O die, we end up with this design, which is a ring of rings. What we have here is essentially a nested topology. At the top level, it looks like a ring, and as you move down, we then have a ring of rings. The only downside to this is obviously, if you scale it even further, is your upstream bandwidth, upstream connectivity. When this thing is being hammered, or at the same time, it's different to when only, say, one core on one ring has full bandwidth to everything else. But this also enables that you can segregate different chiplets, different individual 8-core rings from each other in terms of security, in terms of virtualization. But this is, a different way to connect 64 cores than just simply a mesh. Now, the thing is, AMD's I/O die isn't really a straightforward ring. It looks more like this. Now, this diagram is pretty complex, but if you take these black lines, which are part of the original diagram, and then put another one here, you have what looks like a ring on the outside. And then in the middle, you have essentially 2 flat connections with a couple of other elements in between. This is essentially what we might call a bisected ring. So here we have 8 elements. in a bisected ring in two different bisects. You could have a simple straight across the ring as a bisection, or you can have various ones connected, or you can have a mixture of the two where you have both, but then these are cross-connected. Again, this is all idea of you have some elements that have 3 connections, some elements that have 2. Ultimately, you slightly increase the power, but the trade-off is you get a much lower latency with these bisected rings. So the whole point about this video is saying whether there is a limit to AMD's chiplet design. And if it's a ring, then we have a problem, because rings don't scale much more beyond 8 or 10 cores. We see Intel processors with 10 cores and perhaps a couple of little extras onto those rings. But going beyond 10 cores, Intel doesn't want to do a ring. They would much prefer to do a mesh. So with AMD's chiplets, currently with 8 cores, one avenue is that they go to 12 cores or maybe 16 cores. And if that's the case, they really, really can't do a ring. Now we've kind of seen leaks that AMD's 4th gen EPYC Genoa will just simply add more chiplets. That's a solution. The other solution is they could do 2 CCXs per chiplet again. That means that we still have the 8-core CCXs, but we now have 16 cores per chiplet. There's a mix going on here. And if we look at Intel's biggest ring design that they've ever made, what we have here, the Broadwell Xeon E family. And this is their 24-core product. Now, what we have here is 2 12-core sections, and Intel has decided to split it into 2 rings with this sort of connectivity between the rings. So you have a dual ring design and the connectivity between the rings. So this ring has the 12 cores, has the 2 connectivity stops, and DDR. This ring has the 12 cores, the 2 stops, 1 to DDR, then 1 for chip-to-chip communication, then 1 to PCIe. So that's 17 stops on that ring. And we really, really are pushing the limit of the rings here. Even if you double, triple, quadruple the rings for bandwidth, your main situation in this point is going to be latency. I mean, the average hop to get from, say, this core all the way over to this core, we've got 1, 2, 3, 4, 5, 6, 7, 8 hop, stops on that in that ring. You can see why Intel moved to a mesh. Now, with that being said, I want to go back to AMD's design, because they're saying it's a ring with high bandwidth, low latency. When we asked them at launch, they said, well, it's effectively all-to-all connected. And in our testing, we saw latency that was more akin to an almost fully connected design rather than just simply a ring. With a ring, you get to learn how to spot, the latency differences between the cores. This was much lower than that. So what we think AMD is actually doing is, arguably, yes, they have a bidirectional ring bus, but what they're doing is they probably have got a bisected ring or dual rings with multiple ring-to-ring connections, kind of like that Intel chip we saw. So in these designs, or the third one where you've got these pairs twisted, minimizes the hops, gets you a lower average latency across the ring, across the whole 8 elements. This is good, but again, bisected rings have to scale. And the ultimate vision of a bisected ring, if you take it to, its absolute extreme, is a mesh. And Intel has called its mesh a ring of rings, because essentially each 4-core section, each 4-element section, is a ring in itself. So the question here is where AMD goes from this. If they've got a bisected ring for the 8 cores, and if we take the bisected ring to its ultimate conclusion, what we're talking about is really a mesh, as in rings and rings and rings, and that's kind of what Intel calls its mesh already, a ring of rings. Now, we've spoken a little bit about earlier how if you add in a little bit of 3D into your network design, you can have a multitude of interconnect topologies. And AMD is already kind of playing with 3D stacking technology. They already announced vCache. So this is just adding, L3 cache on top of your chip. simple as in, TSMC's been working on this packaging technology and AMD's integrating it to get more 64 megabytes of L3 cache onto each 8-core chiplet for 96 megabytes of cache. So 3D is possible. What if we take it the other way? So, I mean, this slide that I showed up earlier showing, different ways to interconnect elements on a design. This was actually co-authored by AMD. So imagine a situation then where you have your chiplet, you have your V-cache stacked on top, and then let's put an interposer underneath. And that interposer is where you have your interconnect. So we have your core chiplet. Let's say we have 16 cores in a 4x4 array, or even 20 cores in a 5x4 array. You can now have your cache on top, just as before, but now your interposer underneath does all your networking. So you can actually move your networking off the core chiplet into the interposer. Your interposer might also then have your SerDes link over to the I/O die. Normally, when we speak about interposers, we speak about something with multiple chiplets on top. Say a big GPU and HBM, because AMD has experience with interposer packaging technologies. But I'm just simply saying, let's make it the same size as a core chiplet, and then you put the V-cache on top, and then that's it. You have designed your interconnect for a multi-core chiplet, going beyond 8 cores, going beyond a ring or a bisected ring. Now let's take it further, because I said that interposers can have multiple chips on board. How about we now move to multiple chiplets in this design? What you have is each core chiplet, maybe 8 or 16 cores. You have V-cache on top of each of those, but now you have an interposer underneath. And what this does is effectively make those 2 chiplets act as one. Each chiplet can access the other chiplet's level 3 cache. They can ping pong each other through the interposer without having to go to the I/O die. You essentially coalesce your chiplet design into another abstraction layer. So when AMD announced the V-cache, they said the only extra latency from the V-cache is going to be through additional wire length. In this case, the same is going to be true. Now, your interposer does have to deal with power and data. Now, again, AMD's had experience of that. But ultimately, this is where we could end up with AMD. If Genoa is going to 96 cores, if you imagine Milan with having 8 chiplets, 2 in each quadrant, and we're moving to 3 in each quadrant, imagine if each quadrant had those 3 chiplets on an interposer, and then you could actually have 16 to 24 cores all connected, and then have a high bandwidth SerDes link into the I/O die, rather than having 3 separate links into the I/O die. Now you have more bandwidth to the chiplet, and as long as everything inside the I/O die itself could have an interposer underneath to deal with that network connectivity, and it just keeps on going on. And because AMD's done this paper, they've done the research into which network connectivities work best. I could feasibly see AMD going down this route. But yeah, ever since AMD presented this at Hot Chips, I've been thinking, well, what does it mean long term for AMD? They can't just keep adding cores into the CCX. Going from 4 to 8 is simple enough. Going from an all connected design to that ring or to a bisected ring or whatever they're doing there. But going beyond that, they're going to have to be a lot smarter if they're going to be adding more cores to their chiplets. Now, if Genoa is right, and we've got 6, 8 core chiplets with TSMC 5 nanometer, you could see that in the future they can't just keep bringing the chiplet size down, because then your interconnect power becomes a large chunk of that. If you can move it to an interposer, now the interposer can be built on 65 nanometer. That's no problem, and that's really, really cheap to add. You can then have a dedicated SerDes link between your interposer and your I/O die, and arguably you can scale that down in power-wise and bandwidth-wise if you're not using that many cores. I don't know. My minimum specification here is, yes, this is AMD's next step. We're going to have 3 stacked chip designs with interposer, chiplet, Vcache, and then IO die. Whether any of it comes down to consumer, Ryzen 5950X, imagine if those two chiplets were connected together with an interposer and you didn't have to keep bouncing out to the IO die for core-to-core connectivity. Your IO die simply becomes your access to main memory or to PCIe. That is what makes sense here. If you like this content, please don't forget to like and subscribe. We also have now a private Discord server, and if you want access to that, become a Patreon member and it'll instantly add you as long as your emails are linked. You can join the Patreon for as little as $1.50 a month, and it all goes back into helping the channel. Thank you for your support.